Okay, so now that we've talked a bit about computing limits numerically and estimating limits, we really need to start getting into how do we do this in a more reliable or more quick way, right? How do we do it algebraically or what we would call analytically? Well, in order to get to that step, we have to understand properties of limits and, you know, what we're allowed to do with them. So those are encompassed in the limit laws here that we're going to talk about. So what we need to define beforehand is C is just some constant, any number you want. Positive, negative, zero, a whole number, a fraction, an irrational number, it doesn't matter. Right, so just any number. And then we need these two limits, limit as x approaches a of f of x, and limit as x approaches a of g of x. We need to know that those exist. Okay? And this can be as well, these can both be limits from the left or limits from the right, where you have the minus or pluses up here. These will all apply to that as well. Okay, then what happens? Well, first thing we want to ask, what about the limit as x approaches a of the sum of two functions, f of x plus g of x? Okay. What if we add two functions, then take the limit? Well, turns out that's the same as taking the two limits first and then adding those together. Right. So this is one of those things that sort of, this is what we hope would happen, and in fact, it is what happens. All right, and this is great. Likewise, what happens if you take two functions and you subtract them? Well, it's exactly sort of what we hope it is again. So I'm going to use the magic of copy and paste here, and then make some slight edits to say, yeah, if you subtract two functions, then take the limit, that's the same as taking the limits individually and subtracting those. Right? Another thing, another limit law here, is that if we take the limit as x approaches a of a constant times a function, well then we can take this constant and pull it out of the function and do this. Or sorry, take this constant and pull it out of the limit. So in other words, if I want something like 10 times a function and then the limit, I can do the limit first, then multiply that by 10, and we're good to go. All right. 4. All right, so we have addition, subtraction, multiplying by a constant. Well, why not multiply two functions together? All right, how about the limit of f of x times g of x? Right. What are we going to get out of that? Well, you know, again, there's always a worry in math that do things work out the way we hope they do? This is always something we need to check. But in this case, with limits, yeah, it does. Right? If we multiply two functions, then take the limit, we can instead take the limit of the two functions first and multiply those. Right? Wonderful. Couple more properties here. Right? If we're going to multiply functions, why not divide them? So, what about the limit of this, of f over g? Well, this is, you know, just like with the other one, we're going to get the quotient of the limits. But this one has a little snag to it, a little caveat. Right? What do you think that is? What do you think could go wrong here? So there's one situation in which this could go wrong. So this is true provided that this limit here is not 0. Right? Because if the bottom limit were 0, well, then we'd be dividing by 0 and we'd have sort of a problem, right? But as long as that denominator isn't going to go to 0, then this is exactly right, which is great. Right? So there's one more law here that's sort of a consequence of number 4. So let me add this in as number 6. We'll say here limit as x goes to a of f of x to the nth power is, well, we can just do the limit as x goes to a of f of x, and we can do that to the nth power. Okay. So this is true if n is a positive integer. Right? So if it's any positive integer, like 1, 2, 3, 4, 5, and so on, the counting numbers, then this is true, regardless. Now, this is actually more generally true. It doesn't have to just be a positive number. It can be a fraction. It can be a negative number. But you have to watch out for that. Because, you know, if this is, say, 1/2 and this limit is negative, you're going to be taking the square root of a negative number. So you've got to watch out for that. That would make this not true. If the limit of this were 0 and n were -1, then we'd get 1 over 0. So it's not always true for all functions and all numbers n. So for all functions f and for all numbers n. But we can guarantee if n is a positive integer, this is always true. Right? So just an example of why this kind of stuff is necessary to talk about, why these sort of laws are necessary to talk about. Let's look at a simple limit of a polynomial. Right? I guess let me sort of say real quick that it's probably no surprise to you that the limit as x approaches a of a constant is just that constant itself. Right? If you look at the graph of a constant, it's never changing. So, well, that's pretty true. Pretty straightforward. Oops. I don't know why it zooms in like that. That's true. Another fact that's pretty easy to see is that if we take the limit as x approaches a of x, then that's just going to be a. Okay? So these two facts are easy to verify numerically, or if you go look up the definition of a limit, it's not too hard to verify these two things. I think they're kind of easy to see from a graph. But let's look at why these limit laws are necessary. Right? We want to get to the point where, again, we can just do this algebraically. So let's look at the limit of something like x goes to 2 of 3x squared minus 4x plus 1. Okay? So how does this come into play here? Well, using properties, let's see, 1 and 2, what we can do, I'll say property 1 and 2, we can say, well, this is the limit as x approaches 2 of 3x squared minus the limit as x approaches 2 of 4x plus the limit as x approaches 2 of 1. Okay. Let's use property 3 to say that, well, this is 3 times the limit as x goes to 2 of x squared minus 4 times the limit as x goes to 2 of x plus the limit as x goes to 2, 1. Okay. And then one more property here, we're going to use property 6 to say this is 3 times the limit as x goes to 2 of x squared minus 4 times the limit as x goes to 2 of x plus the limit as x goes to 2 of 1. All right, let me put some parentheses here just to, or just for emphasis. But now we can just use these two basic facts here to say, well, this is 3 times 2 squared minus 4 times 2 plus 1. Right, and so that's going to give us 12 minus 8 plus 1, which is 5. Right. So what does this sort of tell us? Well, if we look in this case, it says, well, you know, we could really just plug the 2 in here, and well, there's nothing to plug in for the 1. But it's sort of saying for nice enough functions, we can just plug in this value of a here. All right? So keep that phrase in mind, though, nice enough function. So you're not going to go through and use these limit laws every single time you do a limit. That would be really tedious. But this is sort of justifying why we're allowed to just plug in 2. Right? And again, provided it makes sense. So we'll talk about that more in the next couple videos.